Hi everyone, myself Dr. Manjunath Asi, working as an assistant professor in the Department of Chemistry, RV College of Engineering, Bangalore, India. In today's lecture, in this video, I would like to discuss about nanomaterials. In the beginning, I'll give you a brief introduction about the nanomaterial and its classification, and very importantly, how these nanomaterials are different than their bulk counterpart, especially the properties like the surface area, band gap, and optical properties, and also the catalytic properties that I'm going to discuss in detail. So what are nanomaterials? How are they different than the macro particles or bulk materials? You can see through naked eye, can you see something here? We can't see anything here. It's just a plane of paper. If you see that spot through naked eye. However, if you see the same spot, this spot using as a transmission electron microscope, you will see the beautiful things inside that spot, and they're called nanomaterials. The nanomaterials that you can see only through using a transmission electron microscope. However, through naked eye, you can't see them. You can't see them. Even if they're present in front of you, we can't see that materials. That much small they are. For example, this is some zinc oxide material, the powder. Through this naked eye, if you see that, it looks like this. It's just a normal powder, like sugar or whatever, that salt. It's look like a salt. It is actually zinc oxide powder. Just like a powder, it will see. However, if you see that using transmission electron microscope, you just place that powder here, and you just using this microscope, if you see that, and you will see the beautiful structures which exist at nano level, and they're called nanomaterials. That is how they're different. And some other materials, it looks like a powder, normal powder, if you see them through naked eye. However, if you see the same powder through electron microscope, you will see the beautiful structures at nano level. See the scale. This is 200 nanometer. It is actually made up of microparticles of that zinc oxide. They're called nanomaterials. Nanomaterials are the materials having the size, having the dimension less than 100 nanometer in all the three axes. Means the size of that any material, if it is less than 100 nanometer, they're all considered as a nanomaterials. Actually, the word nano is originated from Greek language, means nanos. Nanos means dwarf. Dwarf means very small. So, and it is been used as a prefix for the number 10 power minus 9. 10 power minus 9 is also called as nano. Okay. So we know that millimeter, M is the prefix, milli is the prefix used for millimeter. Therefore, for nanometer, we use 10, for 10 power minus 9 meter, we use the word nano. For 10 power minus 3 meter, we use millimeter. Similarly, for 10 power minus 9 meter, we use nanometer. So 1 nanometer is 1 billionth of a meter. 1 billionth of a meter. So let us understand this nano dimension just by taking some example. Example 1, we all know that hydrogen atom is the smallest atom among all the elements, and it is the size of that hydrogen atom is about 0.1 nanometer, means 1 angstrom. Okay, if you arrange the hydrogen atoms, about 10 hydrogen atoms in one line, okay, so the resulting length would be approximately 1 nanometer. So you can imagine that 1 nanometer is almost the length of 10 hydrogen atoms. So you can easily imagine how the nanomaterial or nano dimension. So similarly, 1 nanometer is approximately 5 silicon atoms. So if you arrange 5 silicon atoms in a line, the length of that silicon line would be 1 nanometer. Or another example is that human hair A single strand of human hair is about 20,000 nanometer in diameter. Means the diameter of a single strand of human hair is about 20,000 nanometer. Means you can imagine nanometer is how much smaller than the diameter of the human hair. So it means that almost 1 lakh times smaller than the diameter of human hair. So 1 nanometer is 1 lakh times smaller. Means if you cleave that human hair about 1 lakh times horizontally, you will end up with a nano human hair. Okay, and we all know that the size of DNA, the nucleic acids molecules present in our body is about 2.5 nanometer. So our body is made up of millions and millions of nanomaterials, the organic nanomaterials. So this is about nano dimension. Let us compare the nanoscale with other naturally created materials and as well as artificial that human made man-made materials. So we know that the ant we see is very smallest insect, and the size of that is about 5 millimeter. uh, this is the scale. And if you still go to smaller dimension, you will see that dust mite is about 200 micrometer. This is naturally created species. If you still go down, the human hair is about 10 to 50 micrometer wide, the diameter. Okay, so the human hair is also not, it's not a nanomaterial. Then if you still go down, and uh, you will if you consider red blood cells is also micro in size. So RBC is also greater than the size of RBC is also greater than nanometer. So next, if you go to next level is we will this red blood cells will have RNA, DNA, and the size of DNA molecule is about 2 to 12 nanometer in dimension. So therefore, the nanomaterials, they are coming in between red blood cells, smaller than RBC, and greater than or almost equal to DNA. Okay, this is the courtesy from the Encyclopedia Britannica. This image is taken from that. These are all naturally created materials in which the nano dimension nanomaterials are coming. The size of them are coming between these two. And these are all man-made materials. The carbon nanotube, the diameter is about 2 nanometer. That is also considered as a nanomaterial. And up to 100 nanometer, we call them as a nanomaterial. And this is a quantum coral. 48 iron atoms are arranged in this. This is about 40 nanometer in dimension. This is also nanomaterial. Okay, and this is the microelectro MEMS device, which is for micrometer in size. And the nanomaterials is actually made up of nano materials. So nanomaterials are smaller than MEMS. So like that, you can imagine the size of nano dimension. Okay. Next, let us look at the classification of nanomaterials. How these nanomaterials are classified. Nanomaterials are classified based on their dimension in which they have grown beyond 100 nanometer. So based on that, nanomaterials are classified as 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional nanostructures. 0-dimensional means if the material size is less than 100 nanometer, means 1 to 100 nanometer in all the 3 dimension, x-axis, y-axis, and z-axis, we call them as 0-dimensional materials. Means the size of that material is not crossed 100 nanometer in any of the dimension. So we call them as a 0-dimensional. Suppose if the size of that material is less than 100 nanometer, less than 10 nanometer, we call them as a quantum dot. Quantum dot is also nanomaterial, but its size, the dimension, is less than 10 nanometer in all the 3 dimension. So we call it as a quantum dot. So it is also coming under 0-dimensional material. Next, 1 dimension. If the size of the material has crossed or grown more than 100 nanometer in any one of the dimension, so we call them as a 1-dimensional material. Other 2 dimension of that material, the size of the other 2 dimension in the other 2 dimension would be less than 100 nanometer. So the that one-dimensional material would look like wire-shaped or rod-shaped or tube-shaped. So in which the width and height would be less than 100 nanometer. However, the length would be greater than 100 nanometer. Similarly, two-dimensional material is a nanomaterial in which the size of that is greater than 100 nanometer in 2 dimensions. In 1 dimension, it is less than 100. In 2 dimension, it is greater than 100 nanometer. Therefore, the two-dimensional material looks like a sheets or plates that I'll show you in the next slide. 3-dimensional nanostructures are they're greater than 100 nanometer in all the 3 dimension. However, because that material is made up of the cluster or the combination of the combination of 0-dimensional or 1-dimensional or 2-dimensional, so we call it as a 3D nanostructures. 3D nanostructure, in most of the cases, it is made up of for example, if you take nano flower is greater than 100 nanometer, but however the leaves and as well as petals are actually 2D material. They're all less than 100 nanometer. Such structures are called 3-dimensional nanostructure. Let us understand in detail about the classification of materials with some images. Okay, so these are all 0-dimensional material. They look like spherical particles. Even a small spherical particle, if it is made up of even smaller, the aggregation of smaller particles, they're also called 0-dimension materials because their size is not more than 100 nanometer in all the 3 dimension. 1-dimensional materials are the materials, they look like wires or rods or tubes, tubular structures. They have grown beyond 100. See this one, this is greater than 100 nanometer. However, the width and as well as the height would be less than 100 nanometer. This is 1-dimensional material. 2D means it has, this is greater than, the width is greater than 100 nanometer, and also this one, the length is also 100 nanometer. However, the thickness would be less than 100 nanometer. So they look like a sheets type of structures. 3D is actually greater than 100 nanometer in all the 3 dimension. This is a 3D nanostructure. This is made up of a cube. This is a one particle, but actually made up of many cubes. 9, 12, 3, so 6, almost 18 cubes it is made up of. Each cube is less than 100 nanometer. Okay, so this is one nanoparticle. It is made up of the aggregation of 18 cubes. So this is considered as a 3D nanomaterial. Okay, this is another image showing the differentiation of 0-dimensional, 1-dimensional, 2-dimensional, and 3D nanostructures. This is 0-dimensional material, 1-dimensional, and 2D and 3D. Look at this 0D, most of them are spherical in nature. This is core shell nanoparticles, means there will be a one nanoparticle inside and the surface is being coated with other material, but the size of them is less than 100 nanometer in all the 3 dimensions. So this is encapsulated nanosphere. There are some smallest particles which are embedded in that spherical particle. This is also 0-dimensional material. Okay, this is a composite nanoparticles. 1D is greater than 100 nanometer. Even that you can have the small particles which are aggregated inside. This is a carbon nanotube filled with some other material. This is a 1-dimensional material. Okay, this is how they look like. And 2D, they look like graphene sheets and plates, carbon coated nanoplates, carbon coated nano belts, etc. They're all considered as 2D materials. 3D, they have mesoporous composite electrodes like this. This is actually 1-dimensional material. So this 3D structure is made up of 1, 2, 3, 4, 5, 6, 7 one-dimensional tubes. So it is considered as 3D nanostructures. Here also microporous composite electrode. It's made up of a spherical 0-dimensional material. The aggregation of that would lead to 3D material. So this is a 3D electrode. Okay. So this is how we differentiate 0-dimensional, 1-dimensional, 2D and 3D materials. Next, the very important property of nanomaterial is nanomaterial is completely different than the bulk counterpart because their properties are completely changed. For example, if you take gold is actually yellow in color, but if you go to nano level, its color completely changes. Let us look at why the properties, or that electronic properties or magnetic properties or mechanical or physical or chemical properties of a material changes when its size is reduced to nano level. In bulk, it will show different properties. If you go to nano size, it will show different properties. So what is the reason behind that? Let us understand that first. Okay. We know that nanomaterials structural features are actually, they come in between atoms and bulk materials, because they neither the size of them is more than atom and less than bulk material. Okay. So why the nanomaterials exhibit different properties? Because of these four properties are completely changed. uh, in case of nanomaterial, large fraction of the atoms are exposed. More number of atoms or surface atoms are exposed. Means surface area is increased. If you go from bulk to nano, large fraction of atoms are exposed. And nanomaterials have high surface energy than their bulk counterpart. And nanomaterials are spatially confined. It means that it is also called quantum confinement. Bulk material, when they are reduced, for example, if you break down a bulk material into nano level, the movement of electrons are restricted here. The movement of electrons are restricted. For example, if you take 1 centimeter iron gold rod, that electron can move throughout that 1 centimeter. If you break down into nano, that same electron cannot go beyond a nanometer. Means you are restricting the movement of the electrons. That is called spatial confinement or quantum confinement. Hence, its electronic properties completely changed. And as well as these nanomaterials have less imperfections in the crystal structures. Defects are less, reduced imperfections. So because of these features, nanomaterials exhibit completely different properties than their bulk materials. So let us look at how the surface area of a nanomaterial is changed with respect to its bulk counterpart. When particles are created with the nano dimensions about 1 to 100 nanometers, that can be seen only through electron microscope, the properties are completely changed. And the properties like optical property, electrical, magnetic, chemical properties are completely changed. That is, in most of the cases, it is because of surface area is increased. Nanoscale materials have large surface area than corresponding bulk material. If you take 1 gram of bulk material and 1 gram of the nano sized for nano scaled material of the same type, then the surface area of nanomaterial will be larger than that of the bulk. Okay. So surface area per mass of material increases, greater amount of material can come into contact with surrounding materials. Therefore, its properties and reactivities are completely changed. You can see that in this image, this is the one cube of 1 centimeter cube. The surface area of 1 centimeter cube of this material this is the surface area. Okay, you can easily calculate this one: 1 centimeter square, 1 centimeter square, and 1 centimeter square. There are the 6 faces, therefore the surface area is 6 centimeter square. Only this is the area which is exposed to the outer environment. Means for any reactions to happen, that has to happen only on the surface. Only this will interact. Whatever the material which is inside this cube, that is not exposed. It is stable. Okay. However, if you make that cube into 1 millimeter cubes, 1 centimeter is made into 1 millimeter. The surface area is increased to 60 centimeter square. Means the 10 times it is exposed. Even the inside materials are also exposed. If you make all of them as nanometer cubes, you can see that. You can see the increase in the surface area. All of them are exposed. All the material particles are exposed. So therefore, its property is completely changed. This is another image representing how the surface area increases from bulk to nano level. So therefore, the property of this is different, and property of however the size, the weight is same. If you take 1 gram of this, and this will also 1 gram, but the surface area is very high, and for this the surface area is less. So surface area of nanomaterial is higher than that of bulk material. Along with the surface area, the band gap of material is also increases. Okay, so we know that the band gap is the gap between the conduction band and valence band. So this is a continuous energy levels which are present in the conduction band. Valence band is the electron where the present in the outermost orbital. This is also, there is continuous band. There is no discrete energy levels here. This is the normal band structure in case of bulk material. If they are overlapped, that is called conductor. If the band gap is 0, we call it as a conductor. If the band gap is very large, we call it as an insulator. If the band gap is somewhere between a conductor and insulator, we call it as a semiconductor. If you break that bulk material into nano level, if you cleave that bulk material into nano level, that band gap increases. Band gap increases. See, the particle size decreases. Particle size decreases from bulk to nano, nano to still nano, smallest material. The band gap of the nano material increases. So because of the change in the band gap, its electronic properties are completely altered, because the electronic property depends on the excitation of electron from year to year. Okay, it is becoming from conducting to insulating, semiconducting to insulating. Means in bulk state, it may be semiconducting. If you go to nano level, it may become insulator. Its optical property is completely changed because of the too much band gap. Okay, and also even in the valence band, there is a discrete energy levels. Okay, discrete energy levels. So this is how the band gap is changed for nanomaterial. You can see this is some nanomaterial. This is the band gap. Even from 6 nanometer to 2 nanometer, the band gap increases. The particle size decreases. These are all quantum dot structure, because they are less than 10 nanometer. So this is the band gap of this one. And look at this. When they expose the colloidal suspension of this nanomaterial, visible light, so it exhibits this color. Even 2 nanometer particles present in the solution, it exhibits this color. The optical properties are completely changed because of the change in the band gap. So let us understand in detail why this optical properties changed for a colloidal suspension of metal nanoparticles. It is mainly because of surface plasmon resonance. What is the surface plasmon resonance? It is actually the coherent excitation of the free electrons present in the conduction band of the metallic nanoparticles present in the solution, that they start vibrating, in phase vibration, oscillation with the incident visible light. Means when the metallic nanoparticles dissolved in some solvent or exposed to a light, visible, UV visible or infrared light, that electrons present in that conduction band, they start vibrating by absorbing some amount of energy from the visible light. They start vibrating. They start may produce in-phase oscillation with incident light. They're called surface plasmon resonance. It is actually a surface phenomena. It happens in surface of the nanomaterial. When the size of the nanocrystal is smaller than the wavelength of the incident light radiation, a surface plasmon resonance is generated. Means if you are passing the light of about 200, 400, 500 nanometer, if the size of them is greater than 600 nanometer, say greater than that, then you won't find surface plasmon resonance. In order to have surface plasmon resonance, the size of them should be less than the wavelength of the light that you are passing. Okay. In solid state physics, the plasmon represents the collective oscillation of free charge in a metal. Okay, metal has a charge. The outermost orbital, the metal is covered with electron cloud outside, and inside we have a nucleus. Okay, the collective oscillation of free charge. Free charge is a electron here. Okay, so the positive charge, that is a nucleus, is in the metal is fixed. However, the free electron cloud is free to move around it. An applied electric field in the form of light, because light is electromagnetic radiation that has both electric field and magnetic field. So when you pass that light is having electric field. That electric field causes the electrons on the surface of the atoms to vibrate collectively. So that is called plasmons. That is called plasmons, like this. So this is the metallic nanoparticles which are present in the solution. When you pass the light, electromagnetic radiation, this is the light, visible light or UV visible or AR light, that depends on the size of this nanoparticle. This has an electric field vector. Okay, so this will cause the electron cloud to start vibrate. This is called electron cloud on the metal. It will go down and up. So this up and down, the vibration of this electron cloud requires energy. It absorbs certain amount of energy, and the remaining energy is transmitted. So that color is appeared for the colloidal suspension. If the size of the particle is different, it requires different energy and exhibit different color. If the size of the particle is changes, then that electron cloud which is present on that particle will absorb different amount of energy. So then it will exhibit different color. So this is clearly representing how the electron cloud, this is called plasmon wave, that is vibrating. There is in phase. This is called in phase oscillation with the incident radiation, that is electromagnetic radiation. Since the electrons are also particles with an electric charge, when they vibrate, they also generate electric field. And when the electric field from the vibration of free electrons and the applied external electric field resonate, the resulting phenomena is called surface plasma resonance that occurs on the surface of the metal. However, if light irradiates a solution that contains dispersed metal nanoparticle smaller than the wavelength of the light, then depending on the electric field of the light, the deviation produces free electron at the surface of the metal. As a result, sometimes a weak or thick portions of the electric field appear on a nanoparticle surface and can be considered as a kind of polarization. So we know that nanoparticles absorb visible light and produce surface plasmons. Small nanoparticles absorb blue-green light. Blue-green. We know that in the visible light we have VIB-GIR. Okay, VIB-GIR light. But they absorb some light and reflect the complementary color. If they absorb blue-green wavelength light, they emit red light. Means if the colloidal suspension, when they expose to visible light, if they appear red light, means that they are absorbing blue-green wavelength. By absorbing this radiation, it induces a surface plasma resonance, means the collective vibration, the coherent excitation of that electron cloud is happening by absorbing this wavelength. When the size of the nanoparticles increases, what happens? The size of the nanoparticles increases, band gap decreases. So therefore, the wavelength of plasma resonance absorption moves to longer wavelength. Longer wavelength means red wavelength. Red wavelength means lower energy. Means you require lower energy because the band gap is less to excite that electron in the conduction band. Now the red light is absorbed, blue light is reflected. So resulting in pale blue or purple color for the particles. When the particle size increases towards a critical limit, means if the particle size is still very high, then it may absorb IR spectrum of the radiation and visible light is reflected. So these type of optical properties, the optical behavior of the colloidal suspension of metal nanoparticles can be used in biosensors, in biomedical applications. It should be noted that if the colloidal suspension particles, the metal nanoparticles, if they are spherical, it absorbs at a particular wavelength because the polarization happens symmetrically throughout that on the surface of the material, because it is a symmetrical material and it's spherical. However, if the metal is if it is present in the form of rod shape, it exhibit two SPR modes, one due to transverse and other due to longitudinal excitations. It is because of because it generates that vibration in two ways, the polarization in two ways that I'll show in the next slide. The wavelength of the transverse mode is usually set nearly at 520 nanometer for gold. For silver, it is at 14 nanometer. This is a transverse mode of vibration. This is the energy required for the silver and gold. However, for the longitudinal mode, it absorbs in the visible and IR radiation. Okay, look at this. This is representing the same gold nanoparticles. The spherical, if they're in spherical shape, it absorbs only a particular wavelength and show only one peak in the visible light. Okay, only this kind of polarization you can expect, positive and negative. This is called vibrations of the electron cloud. However, if they are in the form of rod shape or like this, you can expect two types of vibration. One is towards like this or towards the edges. Transverse, or we call it as a longitudinal direction or transverse direction, the polarization of the electron cloud. So these two will absorb different wavelength and show two different peaks. So by looking at the number of peaks, we can say that the shape of the particle is spherical or rod shaped. That is one of the advantage of this. Okay. So the wavelength of the corresponding SPR depends on the kind of particle that I mentioned, and also it depends on the shape of the metal nanoparticles, and also to the extent of aggregation of the metal nanoparticles. For example, the wavelength of the surface plasmon resonance band maximum of a spherical gold nanoparticle is 520 to 550 nanometer. This is the wavelength range at which the gold nanoparticles exhibit SPR, surface plasma resonance. If the colloidal gold nanoparticle solution is now irradiated with visible light at these wavelengths, the visible light corresponding to green color is absorbed. Green color is absorbed and the particle now display red color, that is complementary color that I already explained. Similarly, silver nanoparticle exhibit SBR band at 400 nanometer. It absorbs blue color and transmit yellow color, that is actually complementary color to blue color. Okay, so this is the actual image of the gold nanoparticle when gold colloidal suspension of C. This is the gold which is macro in size. This is how it appears. If you make them into nano size and they're dispersed in a suitable solvent and exposed to light, look at this. This is the smallest size and this is exhibiting this color. And increasing the size, look at this, how it is, how the color of the gold suspension is changing. Look at this, even small change in the size, it is changing the color. So this is 2 nanometers. These are all quantum dots of the gold nanoparticles. This is all because of surface plasma resonance. And look at this silver. This is silver nanospheres, 100 nanometer, this one color. Nano prisms, this is same size. And spheres also 100 nanometer. Because of the shape is different, this is also silver and this is also silver, size is also same. But only because of the difference in the shape, it exhibits different color. This is different color. These are all silver, and this is gold. This is gold, and these two are silvers. Okay, even the smallest size, and this is the biggest nanoparticles, and they exhibit different colors. This is all because of surface plasmonism. This is how the optical property of nanomaterials are changing when you go to nano level. Even it depends on aspect ratio, as I told you. Shapes. Look at this nano rods aspect ratio. If it increases, if the aspect length to breadth ratio, if it increases, the SPR band changes. Look at this, blue to red, it has changed. Okay, if you increase the length. Even the shell thickness, if the shell thickness, it's a core shell nanoparticle, the shell thickness decreases, shell thickness increases, it will exhibit different colors. Means from the colors we can calculate the thickness of the nanoparticles. Even nano cages in which the percentage of the gold, even it depends on the concentration. Okay, so if the percentage of gold increases, its color is also changes. And see, this is the cadmium selenide nanoparticles. 2.3 nanometer is exhibiting this color, and 5.5 nanometer is exhibiting this color. It's all because of surface plasma resonance optical property. Even you can see in this graph, if it is spherical, this is a big particle and small particle. The big particle is exhibiting, the black color one is smaller one. It exhibits only one peak, and the slightly bigger nanosphere, it's slightly shifted, but both of them are giving only one peak. Both of them are giving only one peak here. However, if it is a rod shape, you can see that this one. You can see two peaks because of two modes. One is longitudinal and as well as transverse mode. Because of that, it absorbs two wavelength and emits two peaks here. Sorry, shows two peaks. And if the aspect ratio increases, the length increases, See, they're all same material, but they exhibit different absorption bands. So because of their aspect ratio, the size and shapes are different. Look at this is increasing, and see it is absorbing a different wavelength. This is AR means aspect ratio. If aspect ratio increases, the absorption band also changes. All the three are showing two peaks. This is red is also two peaks. That was about optical property. Next, let us briefly understand the catalytic properties of nanomaterials. So we know that catalyst is a substance which enhances the rate of the reaction in most of the chemical reaction, because the catalyst provides the surface and also the active sites for the reactants to sit and react to yield the product. Okay, the rate of the reaction depends on the number of active sites of the catalyst, as we all know that. If the surface area of nano scale catalyst is larger than the bulk material, therefore you can expect more yield if you use a nanoscale catalyst rather than using bulk material. As compared to bulk catalyst, the nanoscale catalyst of the same material with same quantity has more number of active sites. And also because of unsaturated valencies of surface atoms of nanoparticle catalyst, they catalyze the reactions at much faster rates due to high surface energies as compared to respective bulk partners. Bulk material has lower surface energy and lower number of active sites. Therefore, the nanoscale material is found to exhibit very high catalytic efficiency than the corresponding bulk material. Let us understand with some examples. It's been published in some journals. This is the one of the example I've chosen from Catalyst, this journal published in 2013 by this group. Okay, this is actually hydroformylation reaction of 1-hexene using nano oxide, metal oxide, nano ZNO they have used on rhodium catalyst using this. This is a conversion of alkene to aldehyde. They found that they studied this reaction using nano ZNO on rhodium and also bulk ZNO. Okay, it was found that the highest activity with 100% total conversion and about 96% of the yield of this aldehyde was obtained when they used nano zinc oxide catalyst. Okay. This nano zinc oxide catalyst was found to be more stable and active than the corresponding rhodium catalyst. When they used bulk ZNO along with rhodium, the yield was only 76%. Okay, so therefore, from this experimental evidence, we can say that nano catalyst increases the efficiency of the reaction. Let us understand the catalytic property of nanomaterial with another example. So this is the catalytic hydrogenation of paranitrophenol. Means your nitrate group is converting to amino group. We are actually reducing nitrate group to amine group, paranitrophenol to para-amino phenol, paranitrophenol, para-amino phenol by using a nickel catalyst. Okay, so this study was carried out by this group Yan Du and et al. Published in Applied Catalysis journal elsewhere. They found that the hydrogen ratio, when they used a nano-sized nickel, they found that the rate of this reaction when they used nano-sized nickel is about 15 times faster, higher than that of Rani nickel at similar conditions. Just by changing Rani nickel is generally used for this hydrogenation reaction. Changing that Rani nickel to nano-sized nickel, they have increased the rate of the reaction about 15 times. And also they found that the nano-sized nickel system, when they use for more number of cycles, the nano-sized nickel system suffer just 54% deactivation, while Rani nickel system suffers 80.4 deactivation upon using 6 continuous hydrogenation cycles. This indicates nano-sized nickel is still efficient to catalyze this hydrogenation reaction. So this is the advantage of nano material. These results indicate that the catalytic stability of nano-sized nickel system is superior to that of Rani nickel. So this is the another graph which is taken from this journal article representing. You can see that look at this hydrogenation rate. This is the rate of the reaction with respect to reaction time of this reaction. When they use nano size nickel, look at this rate of the reaction, very, very high, almost, as I mentioned here, 15 times higher. When the B is for Rani nickel. Rani nickel means bulk nickel. The rate of the reaction is very, very less. However, when they use nano size nickel, the rate of the reaction is very, very high. It's about 15 times faster. So from these results, we can say that nanomaterials exhibit very good catalytic efficiency than the bulk counterpart. Okay. So with this, I'm concluding my video. If you have any questions or clarifications, please contact me through this email ID. Thank you.